Our second speaker of the day is Nicola Quercioli, who will be speaking to us on the topological and geometrical properties of group equivariant non-expansive operators and their use in deep learning.
Thank you. First, I would thank the organizers for the opportunity to illustrate my research. Most of the content of this talk can be found in this article that is a joint work with Mattia Bergomi, Daniela Giorgi, and Patrizia Frogini. The aim of my talk is to provide a geometrical and topological framework where any agent capable of acting on a certain dataset, for example, a deep neural network, can be formally described as a collection of a certain kind of operators acting on a dataset. In particular, we studied the space of the group equivariant non-expansive operators, or GENEOS. GENEOS could be interesting both in deep learning and in TDA. In some sense, our ambition is to build networks of GENEOS instead of networks of neurons. We have already made some image classifications experiments where a layer in a convolutional neural networks is made up by GENEOS. Moreover, GENEOS are linked to TDA, and I will show you some results about those links. In particular, TDA tools and persistent homology furnish us a way to compute distances between GENEOS in a fast and robust way. And in the other sense, in general, persistent homology is invariant with respect to the action of the group of all homomorphism of our data. But one could be interested only in a smaller group of homomorphisms. For example, in image classification, maybe you can be interested in only rotations, and only translations. And so GENEOS enable us to select a smaller group of invariants for persistent homology. Well, this is the outline of my talk. And I spoke about equivariance, but why equivariance is important in machine learning? This is a very well-known fact, and the reason is mainly twofold. On one hand, the use of operators equivariant with respect to specific transformations allows one to inject pre-existing knowledge in the system, thus gaining control of the learned operators. On the other hand, equivariance corresponds to the introduction of symmetries in our dataset, hence drastically reducing dimensionality of our problem. Another important aspect is that for us, data comparison is almost never a direct process. It is usually mediated by the comparison of new data produced by our agents. And our ambition is that equivariant operators can model those agents acting on data. In my presentation, I will make these further assumptions. Data are represented as a continuous function on a topological space, since only data that are stable can be considered in applications, and stability requires a metric and hence a topology. Data cannot be studied in a direct and absolute way. We can know them only through acts of transformation made by an agent. From our point of view, data itself are not so important, but only the per data agent matters. In general terms, agents are not endowed with purposes or goals. For us, it's only a black box that takes data and transforms them. Agents are described by the way they transform data while respecting some kind of invariances of the symmetries of those data. In other words, any agent can be seen as a group equivariant operator acting on a function space. And for us, data similarity depends on the output of the considered agent. So now we define what is for us is formally a dataset. Take a set X, and the dataset is a set of bounded real-valued functions. A natural topology we can put on this set phi is the L infinity metric. X is only a set, but we need the topology on X, and hence we define a metric dx on the set X that depends on the set phi. This metric tells us that 2 points at x1 and x2 are distant from each other if and only if there exists a function in phi that distinguishes them. Since the space phi is the central concept in our approach, the topology on X depends on phi, but also the topology of the other object we will define. This topology makes our signal continuous, and in particular, if phi is totally bounded, the topology induced by dx is the coarse topology such that each element of phi is continuous. The next step is to define the group of invariance. And for us, the biggest group of equivariance is this group, out phi of x, that is made up by the bijection that preserve phi by composition on the right. This set, this group reveals to be the group of all isometries that preserve phi. We put on it this extended pseudometric, the out, and with this pseudometric, out phi of x is a topological group, and the action of this group on phi is continuous. In general, we are not interested in the invariance with respect all out phi of x, and we will fix a group G, a subgroup G, of that will be our invariance group. And we will say that the pair phi G is a perception pair. An example of a perception pair could be the following one. Let's consider the space phi of all non-expansive compactly supported function from R2 to a suitable interval AB, and we consider the group G of the isometry of the plane. This perception pair could represent, for example, a space of gray level images. Another important distance in our framework is the natural pseudo distance. So suppose that G is a group of phi preserving self-homomorphisms of X. We define dG as the distance between the orbits of phi 1 and phi 2 with respect to the action of G on phi. And this pseudometric is also stable with respect to L infinity distance. In some sense, the natural pseudo distance dG represents our ground truth. But unfortunately, in many cases, dG is difficult to compute. Nevertheless, in this talk, I will show you that dG can be approximated by means of a dual approach based on persistent homology and group equivariant on expansive operators. Now we are ready to define the space of GENEOs. So assume that phi G and psi H are two perception pairs. A GENEO is a map phi T from phi G to psi H, such that T is a group homomorphism, F is equivariant and non-expansive with respect to the L infinity metric. On the space of GENEOs, we put the GENEO distance, that is simply the distance induced by the uniform convergence. And we will use the symbol F all T to denote the set of all GENEOs. An example GENEOS could be the following one. So we take the previous perception pair, and a simple example of GENEOS is the following one. Let us take a compactly supported integrable function f that is invariant with respect to every rotation around the point, around the origin, and suppose that the integral is equal to 1. The convolution with this kernel is a group equivariant on expansive operators with respect to the identical homomorphism. The space of GENEOS has some good properties. So if phi and psi are compact, so if the dataset are compact, the space of all GENEOS is compact, and hence we can approximate it by a finite subset. And moreover, if the dataset are convex, also the space f all t is convex. And those properties are important if we have the ambition to apply this framework to real problems. Now, I will show you some links between TDA and GENEOS. Persistent homology enters in our framework by means of an equality that allows us to approximate natural absolute distance. So, under suitable assumptions on the perception pairs, the natural absolute distance is equal to a pseudometric that involves bottleneck distance between persistent diagrams and GENEOS. As a consequence, the construction of new classes of GENEOS is an important step in the computation of natural absolute distance. And this fact justifies the interest in the following results about building new GENEOS. So if we take a finite subset F that approximate F all T, we can define this pseudometric DF match that is based on the bottleneck pseudodistance, bottleneck metric. This pseudodistance is strongly G-invariant, is stable with respect to the L infinity metric, and approximate well the natural pseudodistance. Persistent homology provides us also an efficient way for the comparison of GENEOS. In fact, we can define the pseudometric delta GENEO that is based on persistent homology, and this is a good proxy for the GENEO. Now, we spoke about the compactness of the space of all GENEOS, and we need some methods to populate this space. A first simple example is the composition. So if we take two GENEOS, the composition of two GENEOS is always a GENEO. Now, another type of method to build GENEOS is the following one, let us assume that F1, Fn are a finite set of GENEOS from the perception pair phi g to the perception pair psi h. We can define a lot of GENEOS. For example, we can define the translation operators, that is a GENEOS. The maximum operators, that is also a GENEO. We can combine those GENEOS with weighted averages, and is also a GENEOS, or by means of power means, and is also a GENEOS. Those methods could be generalized by the following proposition. So if we take a finite set of GENEOS and we consider L a non-expansive map from Rn to R, we can combine them to build a new type of GENEO. Another important class of operators are the permutant operators. And in some sense, they enable us to use the invariance group as a variable. So for us, a permutant measure is a finite Borel sign measure μ on out phi of x that is also invariant under the conjugation action of G. Assume that phi is contained in a linear separable space, and let H be a measurable subset of out phi of x, such that is invariant with respect to the conjugation action of G. And now we can consider this operator fH that is represented by this integral on H. And this operator is a GENEO from phi G. Those methods gives us also a theorem about representation of linear GENEOs. So if X is a finite set and G acts transitively on X, F is a linear GENEO from Rx G to itself with respect to identical homomorphism if and only if there exists a permutant measure B such that F can be described in the following way with this further technical assumption. Now, before ending and concluding my talk, I give you a takeaway message. In our framework, data are not so important, but only the interaction between data and agents matter. And we should study the topological and geometric properties of the space of these interactions. Now, concluding, we have introduced a topological geometrical model where we can formalize and attack this problem. How we can find efficient methods to approximate a given agent observer by a GENEO belonging to a compact and convex space of GENEOs? This problem leads us to the following open questions. How we can build a good library of GENEOs? How can we find a method to choose a finite set F star of GENEOs that allows for a good approximation of the natural pseudodistance and a fast computation? In which cases we can equip a set of GENEOs, a manifold of GENEOs with the structure of a Riemannian manifold? Could we compose operators to form networks in the same way as computational units are connected in artificial neural networks? And thanks for your attention.
Thank you, Nicola. Please, everybody, unmute yourself and let's applaud our speaker. Do you have any questions for Nicola? So while people are thinking of their questions, in the beginning of the talk, Nicola, you mentioned working on some application related to image classification.
Yeah.
Could you explain that?
Well, we take a specific kind of GENEOs that are convolution with respect to kernel that are invariant with respect to isometries. And then we build a metric learning algorithm to learn the distance between digits. We use the MNIST dataset. And thus we take those operators that we select by this metric learning algorithm, and we put it in a layer, in a convolutional layer, and then we classificate digits. So
is there a learning of those convolutions, or are the
in some
convolutions
sense,
fixed?
yeah, but our kernel are not, because in general, convolutional neural networks are equivariant with respect to translations. Our kernel are equivariant with respect to isometries. So we know exactly we in some sense inject the equivariance with respect to isometries and not allowed to learn equivariance with respect to isometries.
Does that make the learning algorithm computationally more expensive, or?
No, no, I don't think so. For example, in order to train our network, we need only, I think, 40 images, because we inject, because equivariance reduces the dimensionality of the problem.
Interesting. So I have another question, which is maybe a bit ambitious. So you could tell me if you've thought about it. So so there's the standard result in neural networks, this universal approximation theorem, which says that the networks can approximate compactly supported functions. And then there are, for other different kinds of networks, different kinds of approximation theorems that say that, whether or not a convolutional neural network can approximate arbitrarily any translation invariant function. Do you think there is a straightforward approach to a universal approximation theorem for the GENEOs? Let's say, for example, that some network built out of GENEOs of the type you described could be used to arbitrarily approximate any, let's say, rotation or whatever group of isometries of interest, any function that's invariant under that?
Well, this is a very interesting question, and I think there is an article about G-equivariant networks or G-invariant networks, but they consider only transitive actions, and in general we do not have this assumption. And obviously this is our goal in some sense, but it is a long path.
It's a very ambitious question. Anyhow, thank you for the explanation. Any other questions?
Just a follow-up to your question, Elkanan. Although I think my internet's not great. The proof of that universal approximation in standard neural networks is in some sense unsatisfying, I think, because the way the proof goes is they show you can reconstruct a step function, and then they write any function as a sum of step functions. And that's, of course, not how neural networks learn, right? But yeah, I'm curious, Nicola, if you have any conjectures of what, if you want to do a proof along those lines, hypothetically speaking, what might be the analog of a step function? Would you sort of take a step function and then look at its orbit under these actions? Or go ahead.
Unfortunately, we didn't think about that because we didn't formalize what is a network of GENEOs. So before we have to build our networks, and then maybe we can use them to approximate functions.
Thanks.